Karl Pearson's coefficient of correlation, which is also said as a product movement correlation, because we are taking the product of the variables, x variable, y variable, we are taking x into y. Then we are trying to establish the relation between both variables x and y here. So he is this Karl Pearson's coefficient of correlation is used widely. So everywhere, whenever some persons want to find the correlation between the variables, so Karl Pearson coefficient of correlation is used there, because it can be used for any variable here, any kind of data. Here, when we are establishing correlation between the variables, here the measures taken for variables, it may be anything. So height and weight of the students. Height is measured either in centimeter or feet or meter or even millimeters. And weight is measured, the measures of weights are kilo, kg, kilogram or grams. Okay, so here two different kinds of variables. Measures of height is different and measures of weight is different. Then also we can establish a relation between height and weight. So like that here, different measures where they each variable takes different measures here. Sometimes counting may come. Okay. So then also we can use the Karl Pearson coefficient of correlation. So what kind of measure we use to measure any variable that doesn't affect the establishment of correlation here. Here, any kind of measure may be used to measure the variables here. So maybe counting. So number of apples grown in a tree. So where there we count them. And when we put fertilizers, so we can't count the fertilizer. We measure it either in liters or in grams. So again we can establish a relation between there. 1 milligram we put fertilizer and we grown 100 apples. So 2 milligrams, 200 apples. So here anything may be the measures. We can establish a relation. So that is the reason why Karl Pearson's coefficient of correlation is used everywhere in any field. Okay. So here, what is the formula? So when it comes to the data variables, already we learned in previous semester what are the different kinds of data: discrete frequency, ungrouped, and grouped data, and even bivariate. So here we are, when it comes to the correlation, here we are studying bivariate data. So when it comes to correlation between the variables, we are studying bivariate data. So bivariate data, again we can put it in ungrouped data, and we can put it in the form of what here? Bivariate frequency distribution table. So in bivariate frequency distribution table, again discrete, both the variables put in a discrete series, or maybe both are put in a continuous frequency distribution, or maybe mix up of both, one variable in a discrete and one variable in a continuous frequency distribution. So here two different formula we get for ungrouped data and bivariate frequency distribution. First, the formula for common formula. It may be applied for either ungrouped data or grouped data, that is bivariate frequency distribution. So that is and here Karl Pearson correlation is denoted by R. We can put xy here to indicate that the correlation between two variables x and y. So R is equal to covariance of xy, covariance of xy divided by root of variance of x into variance of y. So if you write it symbolically, we can show it as a covariance of xy divided by root of variance of x into variance of y. So as we have taken variance of x and variance of y, we have written root here. So we can reduce it further. So we can simplify it and write covariance of xy divided by sigma x into sigma y. That is standard deviation of x and standard deviation of y. Because variance is nothing but square of the standard deviation. So this is a common formula. But when it comes to the discrete, ungrouped data and grouped data, so for grouped data and ungrouped data, we can expand this formula and we can use that. So when it comes to the ungrouped data, covariance Rxy is equal to, so first here we write covariance formula, summation of x minus x bar into bracket y minus y bar whole divided by summation x minus x bar divided into summation y minus y bar. So here we identify deviation between x and x bar, multiply it with the deviation between y and y bar. So x minus x bar into y minus y bar whole divided by root of summation x minus x bar whole square into summation y minus y bar whole square. So remember the formula here, x minus x bar into y minus y bar divided by root of summation x minus x bar whole square into summation y minus y bar whole square. We use instead of this formula we use another formula, so that is Rxy, that is correlation between x and y, is equal to n summation xy minus summation x into summation y whole divided by root of n summation x square minus summation x whole square into bracket n summation y square minus summation y whole square. So this is the formula for ungrouped data. Remember, we use this formula to calculate the problem, and for this is for ungrouped data. For grouped or bivariate data. So Rxy is equal to n summation of summation xy fxy. So here x, y are both x variable and y variable and fxy. So in the bivariate frequency distribution, we get frequency for both x and y. In the table, in each cell, we get a frequency for both the variables. So that frequency minus summation f x fx. So here this fx, the frequency of x variable, and into summation y fy. So here fy is the frequency belongs to y variables divided by root of n summation x square fx minus summation x fx whole square into bracket n summation y square fy minus summation y fy whole square. So n summation of summation xy fxy. Why summation of summation? Because we don't get summation f xy fxy at in one step. So in two steps we get. That is why summation of summation xy fxy. So that is fxy belongs to both variable x and y, and here x fx, x variable into frequency belongs to x, and y variable into frequency belongs to y variable. So y fy, and in the denominator part n summation x square fx minus summation f x fx whole square into bracket n summation y square fy minus summation y fy whole square. So here in correlation, as it is a product method, the variables may be smaller or maybe bigger in digits. So single digit figures, if we get, it is not that difficult to solve the problems here. But when we get 2-digit or more than 2 digits, 3-digit figures, then it becomes difficult to solve the problems. Because 10 into 10, if you multiply, it give 100. Suppose if you multiply 3-digit and 4-digit number, then just imagine the number of digits we get in a number, the product of two variables here. So it becomes difficult to solve the problem by using a direct method. So to that we try to use, or we try to reduce the digits and calculate the problem by taking deviation method, I can say here, or shortcut method, by taking here the property of Karl Pearson's coefficient of correlation. That is here, when any value, any constant value is either added or deducted from each of the variables, and if any value, any constant value is either multiplied or divided by all the variables, that we say change of origin and change of scale respectively. So when we add or deduct any constant number to all the variables, it doesn't affect the correlation between the variables. So we say here correlation, Karl Pearson correlation here, it is independent of a change of origin. And when we multiply or divide by a constant number to all the variables, again, it doesn't affect the correlation between the variables. So we say here again, the correlation, Karl Pearson's coefficient of correlation is independent of change of scale. So by using this property, we use here formula by changing scale and origin both here. Then our formula we get, instead of x and y here, we put u and v by changing the both origin and scale. So here also, instead of xy, we use u, v. Now we discuss the properties of Karl Pearson's coefficient of correlation. First property, the coefficient of correlation is pure number independent of units of measurement of the variables. That I already said you. So here correlation is purely a number which is independent of the measures of variables here. So variable may be measured by any measurement here. So as I said here, height and weight of the student. Height is measured in centimeters, meters, feet, and whereas weight is measured in grams, kilograms. Milk, liquid is measured in terms of liter here, or milliliter. Okay, so anything may be the measurement of any variable. So irrespective of the measurement, so here correlation doesn't affect here. So correlation is a purely independent of the measurement we used to measure the variables. And second property here, the coefficient of correlation is not affected by the change in the origin and scale. So correlation. So as I said when using the formula here, the correlation doesn't affect even if we change the origin, that is adding or deducting all the variables by any constant value, and again it doesn't affect the correlation between the variables when we change the scale, that is either multiplying or dividing by any constant value. So correlation is independent of change of origin and scale both here. Then third property is the correlation cannot be numerically greater than 1. Numerical, either it may be positive or negative, but we don't get a answer greater than 1. So our answer lies in between -1 is less than 0 and 0 is less than 1. So in between, so our answer, correlation answer is plus or minus 1 or maybe 0. So in between these two values we get correlation. If you get an answer more than 1, that means calculation is wrong. In no way, in not in a single situation, we get answer more than 1 here. Numerically less than 1 answer we get. Then last property is interchange of the variables. So here always we can refer here formula. Everywhere I have written x and y. First x and then y. Here also x first and y next. And here also x first then y. Even if we interchange it, y and x, here also summation y into summation x, and here summation y, n summation y square minus summation y whole square, then n summation x square minus summation x whole square, then also result doesn't affect. So here we can say rxy is equal to ryx. Even if we interchange the variables, then also the correlation between the variables remains same. Okay, now I said here the answer lies in between plus or minus 1. So based on that here, how to interpret the correlation between the variables? So interpretation means here the positive value of r indicates the positive correlation. If you get the positive answer, then it is a positive correlation between the variables. If we get a negative answer in between 0 to -1, then we say there is a negative correlation between the variables. Then if we get exactly perfect positive, that is a +1, then we conclude it as a perfect positive correlation. If we get exactly -1, then perfect negative correlation. And if we get r is equal to 0, then non-correlation between the variables. And if your answer is greater than or less than 0.5, low degree correlation, 0.5 to 0.8, moderately correlation, and above 0.8, high degree. If answer is positive, high degree positive. Answer is negative, high degree negative correlation. Okay, so these are the few properties and interpretation of the correlation. Now limitations of correlation. So what are the limitations here? So first, correlation coefficient always assumes linear relationship regardless of the fact whether that assumption is correct or not. So linear assumption means here which doesn't change. So once we conclude that the price and demand have a positive correlation, then always we assume that there is a positive correlation between the variables. Okay, and second, great care must be exercised in interpreting the values of this coefficient, as very often the coefficient of is misinterpreted. So here, if a minor mistake happens, okay, then relation may also get changed here. And the next, the value of coefficient is usually affected by the extreme items. Extreme items. Extreme items means sudden change or huge change. Yeah. So x variables takes 1, 2, 3, 4. Then y takes 4, 5, directly 15, 100. So such changes here, extreme values, they affect the correlation between the variables here. And last point, as compared with the other methods, these methods take more time and compute the value of correlation coefficient. So as here product method, huge calculations we have to make. So it consumes more time to calculate the correlation between the variables.